Experiment number 6 from Design and Analysis of Algorithms Laboratory is to implement a Java program to depict the working of 0-1 knapsack problem using dynamic programming. We have created a class called prog6 in which we have declared a two-dimensional array V of the type integer to hold 40 integer numbers, wherein V stands for the solution vector and there is a function called as max1 to which we pass two integer numbers as parameters in the variables a and b, which returns us a greatest value. So then in the main function we have declared a single dimensional array P which holds the profit of including the items into the knapsack. So P is a single dimensional array defined with a capacity to hold 20 integers. And the next comes a single dimensional array W with a capacity to hold 20 integer numbers, which represents the weights of the items to be included in the knapsack. And then we have declared the variables I, j, n and max. So I, j are used for iterations, n is the maximum number of items and that you want to have in the problem, and max is to hold the maximum value that is being obtained. So in is an object of the type scanner. It is used to read the values from the user. So then the next line sysout asks the user to enter the number of items. So whatever the user enters is read using a method nextInt with the help of the object in and is assigned to the variable n. So if I say n is equal to 5, then the next for loop would run from 1 to 5 and would ask the user to enter the weights and the profits of items ranging from 1 to 5. So wi is equal to in.nextInt is a line which reads the weights into the weight matrix W. Similarly, p of I is equal to in.nextInt is a line which reads profits into the array P. So then once it's done, we ask the user to enter the maximum capacity of the knapsack. So whatever is entered with the help of in.nextInt method is assigned to a variable max. And in the solution vector V, we initialize the 0th row and 0th column with all 0 values there. So therefore, for I is equal to 0 to I less than n, V of I 0 is set to zeros. So it means that all the values in the 0th column are set to 0, and the next for loop sets all the values of 0th row to 0. And then for I is equal to 1 to I less than n, and for j is equal to 1 till the maximum capacity of the knapsack, there are two conditions that are to be tested. So in case if the weight of a particular item that you are trying to include is greater than the capacity of the knapsack, if it is greater than the capacity of the knapsack, then the value of the optimal subset is defined by Vij is equal to V of I minus 1 j. So we assign whatever is the value in the row and the column Vi minus 1 j to the value in Vij. Else, if among the subsets that do not include the ith element. An optimal subset is made up of items and optimal subset of the first I minus 1 elements, first I minus 1 items that fit into the knapsack of the capacity J minus W. So the value of such an optimal subset is given as max of Vi minus 1 j comma summation of whatever is the element at the location V of I minus 1 j minus of the current weight of the item plus its profit. And then once we come out of the for loop, we print the maximum profit obtained, which is at the location V of n comma max in the solution matrix V. So it is nothing but the very last cell, the last row, last column cell which contains the maximum profit in it in the given matrix. And the items that are selected from the given set of items is obtained using this for loop. We try to print them. So for I is equal to n to I is greater than or equal to 1, we go on decrementing the for loop. If the element at the location V of ij, that is the value of an element at the location V of ij, is not equal to the value of element at V of I minus 1j, then we are trying to select this item and place it into the knapsack. So therefore we display the value of the item, and then from the capacity of the knapsack, that is j, we subtract the weight of the currently chosen element. So therefore the line j is equal to j minus w of I is implemented. So this for loop goes on and goes on until it finds all the number of all the different items that fit into the knapsack of capacity j. So line number 42 and line number 40 give us the recurrence relation for including or discarding the elements into the knapsack. So now let us run this program and see how does the output look like. So it is now asking the user to enter the number of items. Let me say there are 4 items, and it is now asking the user to enter the weight and the profit of the first item. So weight of the first item is 2 and its profit, let it be $12, and then the weight and the profit of the second item. So let me say the weight of the first item is 1 and the profit is $10, and then the third item's weight is 3, its profit is $20, and the weight of the last item is 2 and its profit is $15. So the net capacity of the knapsack, let us assume it to be with the capacity to hold only a weight of 5 kgs. So then we see that the maximum profit obtained is 37 and the items that are selected are 4, 2 and 1. So this is how 01 knapsack using dynamic programming works.